In this video, we will be discussing static equilibrium using 3D problems. In our previous video, we talked about static equilibrium in 2D problems using 3 different equations to solve for 3 different unknowns, which included our sum of Fy forces, sum of Fx forces, and some of our forces at a moment about a certain point. In 3D problems, we are going to introduce 3 more equations that we can use to solve for 6 unknowns total. So we're going to have a sum of Fx, Fy, Fz forces, as well as moments about our x-axis, y-axis, and z-axis for a total of 6 equations for 6 unknowns. So if I were to define what I mean by that, so we want the sum of all of our forces to equal 0. So if I wrote this in a Cartesian format, we would want each of our components in our directional representation to equal 0. Or in other words, our sum of Fx equals 0, sum of Fy forces equals 0, and sum of Fz forces equals 0. In addition to that, we also want our total moments to equal 0. So that's to say that our moment about our x-axis plus our moment about our y-axis plus our moment about our z-axis is equal to 0. So that means each component must equal 0 itself. Okay, so we'll talk about some restrictions later, but we now have 6 equations to solve maximum of 6 unknowns. Right? So you can know if you're doing a question correctly or if a question is unsolvable in this regard, because if you're given more than 7 unknowns, then you're going to have a problem because you won't be able to solve it with your 6 equations in this kind of scenario. Okay, we're going to do a bit of a recap about how reactions and moments develop. So we talked a little bit about this in our previous lecture using the 2D problems. So in this video, we'll cover how moments and our forces in a 3D space contribute to all of this. So reactions develop from restrictions in movement. And specifically translation. Right, so that's to say that if we use our 2D example, if I have a beam on this hinge, that would develop X and a Y reaction, which we already covered, because if it's secured to the ground, then this means we can't drag and move that pin to the side or lift it up and down, right? So just think about taking a piece of wood and drilling it into the ground, right? You can't move that piece of wood up from the ground, and you can't move it side to side while it's on the ground. And moments, on the other hand, develop from restrictions in rotation. So in these problems, we're going to be developing pin support reactions as well as moments due to certain fastenings and structures that we use to secure rigid bodies into place. So we're going to have to consider moments that develop, and we also have to consider what direction they are going in. So, like our previous video, we have different kinds of connections and the different kinds of reactions that they produce, as well as the number of unknowns that we produce. So some that I'm just going to skip over really quick. Cables we covered in the last video. So the force just points in tension along the cable. For smooth surfaces and rollers, we just have our normal forces. So those ones are okay. We don't have to worry about these ones. Okay, so next we have a ball and socket. So if you picture a ball and socket, so think of it as a joystick, right? So a joystick in a video game, you can't pick it up, you can't move it, like translate it like side to side or up and down, right? And you can't move it in upwards or downwards direction. It's just fixed to the arcade console, right? You can't do anything with it. It just stays in that same position. So because of that, because there's no translation of the physical thing itself, right? Because this socket is attached to the surface, we can't physically move this piece when we are working with it. So therefore, we develop three unknowns in our fx, fy, and fz direction because we are restricted movement in those places. However, using that same joystick analogy, you can rotate it in any direction, right? You can spin it in any direction. And so because of that, there's no moment developed. So we only have three unknowns just due to the fact that it is fixed to the bottom of wherever it is attached to. Right, so there's three unknowns. Okay, so for a single journal bearing, we cannot rotate it about the z-axis, and we can't rotate it about the y-axis. Is that y? About the x-axis. Sorry. So this is, if we establish this as, say, y, x, z. So, but because this rod runs along the y-axis, it can still rotate. I'm trying to think of a good example to describe this. I guess a pencil sharpener would be a good example, right? So when you sharpen your pencil, you can rotate the pencil while it's in that slot, right, as you're sharpening it, but it won't rotate to the left, it won't rotate to the right, it won't rotate up and down, right? Once it's through there, then it only rotates in the direction to help you sharpen it. You can rotate it just along that plane. So that's why there's no moment developed in our along our x-axis. So, and there's only two other force reactions that are developed because using the pencil sharpener analogy once again, you can sharpen your pencil and you can stick the pencil inside and still pull it out, right? So because of that restriction, so because of that, movement is not restricted along that same axis where there is no moment, which is our y-axis in this case. So there's no Fy and there's no moment about y. So we only have four unknowns in this case. Okay. So in this case, we are picturing that we can't move our pencil. So a circular shape like our previous example allows for you to rotate it. But if you have a shape that has corners and it's set in place and you cannot rotate it, then this creates five unknowns, so there's no Fy. So in this case, you can still stick the peg through the bearing, right? But if it has a square shaft, you cannot rotate it while it's in that hole. So because of it, this lack of rotation, this restriction in rotation, produces our moment at y now, but we still have no Fx because we can still insert the shaft through and still pull it out. Okay, in our next one, now we have five unknowns still, but this is saying that like we cap the ends on either side, right? So now we can no longer insert it all the way through once it's in there, it's set in that place. It can still rotate, but it cannot get pushed in or pulled out any further. So because of that, that restriction develops an Fy reaction, but because it can still rotate, we don't have a moment about y. All right, single smooth pin. Let's see, so it can rotate about this is y, x-axis. So it can still rotate about our x-axis, right? Because if we move this side to side, then we can still picture it like this, right? We could still move it side to side along our x-axis, so there's no moment about x, but because we can't lift it off the ground, we can't move it backwards, move it forwards, or move it side to side, that produces our 3 force reactions and 2 moments about z and y because we cannot rotate about those axes. Okay, looking at a hinge, we have, okay, so once you drill your hinge into your door or wherever you're fastening it, you cannot move it where it is, so you can't move it up, you can't move it to the side, you can't move it forward, right? It's already drilled in. But it allows for rotation over our x-axis, so you can kind of imagine it, sorry, our y-axis, so you can kind of imagine it looking like that. So because of that, there is no moment at y, but there are moments in our other 2 directions and force reactions in all 3 directions. And finally, our fixed support is the only one that will have 6 unknowns because think about like taking a peg and hammering it into like a piece of furniture where it's meant to stay fixed, right? Because you want to be able to fasten your furniture together without the peg that's joining it to rotate. So because it's fixed there, you can't rotate it in any direction and you can't translate it in any direction. So therefore, it produces 6 unknowns in all 3 of our directions. So that covers kind of the logic behind how each of these reactions are developed. So we're going to make this a little more apparent with an example. So we have a smooth collar at A and a roller at B. So we're going to draw the free body diagram for this. So I'm just going to draw this on the side. Free body diagrams don't have to be this complex. I just want to do it to show the geometry a little better. Okay, and we have a collar here at A. And we have a roller here at B. Okay, so let's start with some things that we already know. We know that from rollers, it's the same as 2D problems. It's only going to produce a normal force perpendicular to the surface it's acting on. So this is going to look like this. I'm going to call this By. So that is our first reaction force. And it wants our reactions at point A from the collar. So if we can picture this collar, imagine taking this collar and being able to slide it back and forth along this surface, as if you were sliding a bead along a string from a necklace, right? You could still translate it side to side. So this is our x-axis. So this means we're going to have no Fx reaction because we're not restricting movement in this axis, but we can't move it this way or that way, and we can't move it up and down, right? Because it's fixed there, we can't pull it up and we can't move it move it forward or backward. So because of that, we're going to develop 2 reactions. We're going to develop an Fz reaction. Again, just assume the direction you want, and an Fy reaction. Okay, we're going to establish that this system is positive when they're pointing in these directions. So we have 2 reactions for our A. So therefore, we have Oh, sorry, hold on. So we have 3 unknowns for 6 equations, which means we can definitely solve this. So I'm going to include these in blue, right? And we're going to get started. So let's start with our z direction. So this is equal to, so we have 800 pointing down. We have 600 newtons pointing down. Sorry, this is in our z direction. And we have positive bz and positive fz. So we probably won't solve this equation first because there are a lot of unknowns to work with. But we know in our x direction, we don't have anything pointing along here, so this is just 0. Our fy direction, we just have our, sorry, this, I'm going to say ay. And since ay is our only force, then we know ay is equal to 0. So this is our first one solved. And let's develop an equation that looks a little better for this one. So let's move our 800 and 600 over. And this is 1400 is equal to bz plus az. I'm going to call this equation 1. Okay, so we've already solved for one of our reactions. So now we're going to introduce our moments. So we're going to start with our moment about x, and we want that to equal 0 in the end. So basically, we want to look at all of our forces that don't intersect our x-axis, right? So if I'm drawing AZ and AY, we can see that they clearly go through our x-axis here, right? So we don't want to use those. So this already eliminates 2 of our unknowns to include in our equation, right? But the ones that we can include are going to be BZ and our 800 and 600 Newton forces, external forces. And we just want to measure, since they are on the same plane, we just want to measure the y distance to our x-axis. So measure y distance to x-axis. Okay, so this means for 800 newtons, we're using this distance. For 600 newtons, we use this distance because that's how far it takes to get to our x. And for BZ, we are using this distance, which is the same as 600, right? So it doesn't matter about the other kinds of geometry that's going on, just how far would it take to translate them, just to slide them over towards the x-axis along our y-axis. Okay, so this means that we will do, so I'm just going to start with each one separately, and then I'm going to talk about direction later for our signs. So this is 0.8 meters. For here, we have 600 newtons, and this is 1.6 meters away, and we have BZ, which is also 1.6 meters away. So now we only have one unknown in this equation, and this is all equal to 0. Okay, so like I said, I'll talk about sign now so we know where to put, what sign each term should have. So the first things first, you're going to use right-hand rule, and you're going to point your fingers along the direction of your force and curl it towards the axis you are measuring at. So use your fingers for the force, and then curl to your axis. right, so we're measuring at the x-axis. So say if we did that for 800 newtons, I'm going to draw our hand here. So this is our thumb of our right hand. It's kind of a difficult view to see, right? Let's see if I can draw it a little better. So here's our 800 newtons, and we want to point our hand in the same direction, our fingers in the same direction as our force, so then our fingers point down, right? And when we curl our fingers towards the axis that we're measuring, which is here, that's going to look like this. Right, as our fingers curl towards our x-axis, like that. So then the third part is that our thumbs is going to point in the direction that our moment is acting. So because we established this was our positive x-axis, and after we do this, our thumb points towards the negative part, then this means that we are going to assign a negative sign to this first one here, right? So thumb points in the negative direction. I hope that's kind of making sense. So you're going to look through the positive end to see where your thumb's pointing. So again, if we do that for our 600 force, our hand's going to point down with our 600. We're going to curl our hand. Oh, sorry, this is disturbing. Right, our hand curls. Our fingers curling towards our x-axis, and we see that our thumb points in, again, the negative x direction. So that is negative once again. And now for our BZ reaction, we're going to point our fingers upwards now in our right hand. And when we curl our hand towards our x-axis, that leaves our, oh, sorry, drawing the wrong hand. So we're going to point our fingers with the BZ. Then we're going to curl our fingers towards our x-axis. Right, and when we do that, we see our thumb points in the positive x direction, so that's going to assign this a positive coefficient. Right, so let's do this for our other ones. This is it for mx, my. So we can use anything that intersects y axis. So again, we can't use our az, and definitely not our ay, because they are going through. We can see that 800 also goes through, so that is a no-go. So that means we are left with our 600 and our BZ to use for this one. So let's do that, and we're going to take the x distance that we need to get to our y-axis. So it's going to be this distance here. So this is 600 times 0.4 meters. And we'll add our signs later. And this is BZ. And how far this? This is 0.8 meters from our y-axis. Okay, and now we're going to talk about our direction. So we said that this was our positive, we just keep that there. We said this was our positive y and this was our negative y direction. So by that standard, if we again point our fingers along with our BZ, so this is an open palm here. So this is our right hand pointing with Z, and we curl them towards our Z axis here, sorry, our Y axis. Right after we do that, that means our thumb is pointing along the positive Y axis. So that means we have positive. And for our 600, so this is going to be head on of what our hand looks like. I'm going to point down. Oh, sorry. Let me try and redraw this. Yeah, so we're going to point it down with our open palm. Right, and then you're going to grab it from underneath if you're to wrap your fingers around. So this is like this. And that leaves your thumb also pointing in the positive direction. So that is positive. Sorry, again, I drew the thumb pointing in the wrong direction. Sorry, thumb points this way. Thumb looks like that. Okay, so that means our thumb's going to be pointing in the negative Y direction. So that's going to be negative. Sorry about the confusion. Okay. So that is our moments about our Y axis done. Okay, and last we have about our ZX axis. So we can't use our AZ or AY. And we can't use any of our other external forces because they are parallel to our Z axis because they're all acting in the Z direction, right? So we cannot use any of those. So that means we know the answer for our moment about Z, and that's just equal to 0. Okay, so now I'm just going to solve for our unknowns. I'm going to solve over here. So let's start with our mx equation. Right, if we move these to the other side, this is equal to 1.6 bz, and this is 800 times 0.8 plus 600 times 1.6, and this is equal to 1600 divided by 1.6, and this is equal to 1000 for bz. So there is our first answer. Okay, now let's do our moments about our y-axis. So again, that leaves bz times 0.8. Remove this 600 times 0.4 to the other side. This is 240. And bz also should be equal to hold on. Sorry, that's on me. My bad. We did actually miss an unknown this whole time. I'm so sorry. Right, let's see. So we can still rotate this about our x-axis, I believe, at our A. Sorry, okay. I did forget to add a moment that develops. So we'll do that in yellow. Right, and this develops in our MY direction because if you were to pick up this pipe here, you could still rotate it around the collar about the x-axis as well as the y-axis. So, oh, sorry, and not the y-axis, sorry, not the z-axis. Oh my goodness. So this also develops a moment at z. I'm so sorry. Okay, I can't believe I let that slip through. So in that case, we have just the moment at a z, but that's still going to be equal to 0 because it's the only one that is happening around in that rotation. And now that we have our my, this is added to our my equation. And the reason it's positive is because we assigned this as our positive y-axis. So if we were to take a look directly down this axis, so this is our I, if we were to look directly down, we would see that it'd be rotating in a counterclockwise direction. And in that case, that means I have to change this counterclockwise direction. Okay, so now with that we can solve. Okay, so let's isolate for the MAY, so moments about AY is equal to, this is positive 600 times 0.4, so it's 240, and minus, we found out what BZ was, so that's 1,000 times 0.8, and that's minus 800. So this value is equal to 240 minus 800, and this gives negative 560. And the reason it's negative is because the direction we first assumed is not correct, so that means it is in our clockwise rotation. Okay, and lastly, we are solving for what was it, AZ. So let's use our FZ equation. So then this would be, so we have 1400, and we found what BZ was, so that's 1,000 plus AZ. And if we move that over, AZ is equal to 400 newtons in the same direction that we first assumed. Right, and there are all of our answers, which are highlighted in green boxes. So we have 1, 2, 3, 4, 5 unknowns that we developed in this example. Okay, I will be more careful with the next one about moments. Okay, so our next example has this pipe here, and we have smooth journal bearings at A, B, and C. Smooth journal bearings was like our pencil sharpener, so they can, they're not fixed, so they can slide through, and they can rotate in that same axis. So because of that, let's start drawing some reactions. So we can't move our A in the Z direction, we can't move it up, and we can't move it in our, X direction, but we know our pipe can still slide back and forth in our Y axis. So we have those two there, so AX, and moments I'm going to do in pink. So we don't have any moments about this axis because we can still rotate our pipe in there. So that means we're going to develop an AZ. But in reality, we actually have no moment here, because when you have smooth journal bearings that are perfectly aligned, so when aligned, the body is secure and there's no moments developed. Okay, so because of that, we're only going to focus on force reactions. So in our B, same thing as our point A, because we are on the same axis. It's supposed to say B. And for our C, we can imagine our C sliding through our X, so we have CY and CZ. So we have 6 unknowns and 6 equations to solve them. So let's start with that. I'm going to decompose this 450 into its Y and Z components. So this is at 45 degrees. So this is, I'm just going to say F. So, sorry. Okay, this is 450 cos 45 for our X, and this is this is positive 318.198, and that's going to be the same for our Z component. Okay, and we also have another moment that is a part of the system here. Okay, so let's start building our equations. So we start with our X forces. So this is just AX, our positive X direction, if this is our positive direction. And we have BX equals 0. So first one out of the way. Next we have sum of FY forces, which is just our CY and our component, 318.198, equals 0. Both are in the positive direction. And our Z sum, which is AZ plus BZ plus CZ, and minus our component, and that is equal to 0. Okay, and now let's do our moments. So I'm going to go a little quicker through this one. So we can't use AZ and AX because they go through. BX is parallel, so we can't use that one. So we're going to start with BZ, and that is at a distance of 0.8 meters away. And with our right-hand rule, our thumb points in the positive direction. Okay, we can also use our Y component. Actually, no, we can't, because if we, wait, can we? No. Yeah, we can. Sorry. Oh my goodness. And we just want the vertical distance to get to our x-axis. So we're going to use this distance here that separates them, because then it'll be in line with our x-axis. So this is for this component here. And this is multiplied by 0.4. And this is in our negative x-axis direction. Now we have the Z component, of that same force. And this is pointing downwards. And that means we are pointing in the negative x direction. And this is at a y distance of 1.2 meters. Okay, and we have our cy, so we want to find how far down we need to go to get to our x-axis. So this is cy, and that's multiplied by 0.4, and this is in our negative direction. And finally we have cz, and we're going to use our x direction, our y distance to get to x. So this is 1.2 again. It's pointing upwards, and this is in our positive direction. Okay, so this one has 3 unknowns, so maybe we will not use that one for now. Okay, and in our about y, a lot of things are going through y. So all of these, so az, ax, bz, and bx are all going through y. So is both the components of our 450 newtons, right? The z component's going through, and this component is parallel, and this component is also parallel in our cy. So we can only use cz. It's equal to cz times, and what is this? So this is how far do we have to go to be in line with our y-axis. So then this is our x distance of 0.6. And we also have a moment here, and this is our positive y direction. If we look down the barrel from our positive side, we would see that this is in a clockwise direction. So this is minus our 300 moment, and we want to find the sign of cz. So cz is in the positive y direction as well. So we could solve for cz right here because we have the value for it. So then cz is equal to, so this is 300 divided by 0.6, and this is 500 newtons. Okay, so that is our first value answered. Okay, next is about our z-axis. So what can we eliminate? So we can't use az, bz, cz because they are all parallel. Ax goes through, and this component is also parallel, so we can't use that. So we can use bx, this y component, and this y component here. Okay, so again, we can't use, these are parallel, and this goes through it, so we can only use 1, 2, and 3. Okay. So this is equal to, so we want to find our bx, and it's at a distance of 0.8 to our z-axis, and this is in the this will take a while. Okay, this is in our negative z direction. Okay, So that is our first one. We can do our y component. And this is at a distance of, so it's it's in the y direction, and we're measuring to our z axis, so that means we are using our x distance. And we actually can't use this, sorry, I forgot. We can't use this because if we draw the line of action, it actually goes through our z, so we can't use this one either. Okay, so that just leaves cy, so that is good for us because, sorry, it reduces our unknowns. So this is cy. So it's with y, we want our x direction, our x distance, sorry. So this is 0.6 to our y-axis. And if we point our fingers along, we see that our thumb points down when we wrap around our z-axis, so this is negative. Okay, so there's a lot of different equations, but I would like you guys to practice solving on your own. I'm just going to write out the answers so you can find how to get them. So this is AZ, BZ, we found CZ, so I'd like you to find, what else we got? We've got CY, we've got one more, we've got BX and AX, BX and AX. So do this on your own and see if you get these answers. Okay, so CY is negative 318.198. That should be easy enough to solve. BZ is, hold on. So this is 90.902 newtons. And this is negative 238.648. Then this is negative 272.704. And our last one is equal to positive 238.648 newtons. So see if you get those answers with these equations. If not, let me know and I'll see what corrections I can make. All right. So last part I'd like to talk about is constraints. So for a 2D system, if you recall, you can have 3 unknowns, maximum, and 3 equations. So if it exceeds, then you cannot determine the system. It's non-determinant. And similarly, in a 3D system, you have 6 unknowns max because you have 6 equations you can use. So a system is indeterminate if number of unknowns exceeds equations. Okay, so that's just an important rule to note. Okay, so in our next question, we're going to be talking about some example questions that relate to 3D equilibrium. So come back and we will go through those, and I hope you enjoyed.